Hi, it's Dr. Khan with 5.3 and 5.4. We're going to talk about how we locate the center of an earthquake, the epicenter, and then talk about the different scales that we use to measure how strong an earthquake was. So, first, we're going to start with this image that kind of gives us the end of the story of how it is that we find where an earthquake is located. But it's important to understand this concept of triangulation. So, what we're going to do is look at the seismogram that's produced by a seismograph at different stations. So, we have one here in New York that's going to pick up on an earthquake that occurred. That same earthquake is going to be recorded at a station in Nome, Alaska, and that same earthquake will be picked up in Mexico City. We'll get into how we know the distances in a minute, but for now, if we look at the seismogram, we can look at the data and find out that the earthquake must have happened 2,300 miles away from New York. Again, that's information, and we'll talk about how we get that in a moment. But that's all we know from that seismogram. In other words, we can't tell what direction the earthquake occurred from New York. If we plot all the possible points of the earthquake that are exactly 2,300 miles away, we end up getting a circle with a radius of 2,300 miles. So it could have occurred anywhere along this red circle here around New York. So helpful, but not entirely. We need to narrow it down a little bit. So from there, we go to Nome. We do the analysis of the data at the Nome station, and we find that the earthquake occurred about 2,750 miles from Nome. So we'll draw a circle with a radius of that distance, and we end up with two possible points of intersection between our New York radius and our Nome radius. So the earthquake either happened up here or down here. So it's the addition of the third seismic station that gives us that data from Mexico City. It occurred 1,800 miles from Mexico City. We draw that radius around and we'll find one point of intersection, and that is our approximate location for our epicenter. So we need at least three different seismic stations to have recorded data for that earthquake, and analyzing those three stations give us our epicenter. But we also, in order to get there, we need to look at our seismogram and get information about the time it took for the P wave to arrive versus the S wave to arrive. Remember, P wave, primary wave, that's a seismic wave that travels the fastest velocity. The S wave travels a little more slowly. So we're going to look at the arrival time between the P wave and the S wave in order to estimate that distance. The way that works is we know how much faster the P wave is from the S wave. So they start off in the same place, right? The earthquake happens, and then gradually the P wave will move farther, faster. So knowing what that relationship is between time and how far ahead the P wave is expected to be, we can actually estimate our distance from that epicenter. Then again, we'll draw circles, we'll get the intersections, and we'll be able to approximate that. This is one of the activities that we'll be doing together. So the three seismograms that we saw in the first image there, here's New York. And if we count the arrival time of the P wave where we first see that shaking happen, we can see it's 1 minute, 2, 3, 4, 5 minutes between when the first P wave arrives and the first S wave arrives. So we take that information over to this time travel graph and find the point where the P wave curve and the S wave curve are 5 minutes apart from each other. So this distance in this black line here represents 5 minutes apart. At that location where they're 5 minutes apart, we can read down the graph for kilometers, up the graph to get into miles, and that location that's directly down will be our distance from the seismograph and the epicenter. That gives us that first radius to draw around New York. The second station's data will do the same thing. We'll count the arrival time distance between the P wave and the S wave. So we have 1 minute, 2 minutes, 3 minutes, 4, 5, 6.5 minutes. So as you can probably guess, this station is a little bit further away from the epicenter compared to the actual first station, our New York station. So what we'd have to do is find where these two lines are 6.5 minutes apart, and then again read up or down depending on kilometers or miles in order to get our distance to draw the radius from Nome. We'll do the same thing in Mexico City. What's the difference here? It's a little closer. It looks like 1, 2, 3, 4 minutes between the first P and the first S wave. So we'd expect that to be somewhere around here. We'd find where that 4-minute difference is and read down in order to get the distance. So how do we determine how big an earthquake was? So we can look at something like the intensity of the earthquake, which looks at how much shaking based on how much damage there was. So looking at built structures, human built structures, how much damage was there? So that's often measured using a scale called the modified Mercalli scale. And that's Roman numerals from 1 to 12 that talks about like, did everyone feel it? Did some people feel it? Were certain buildings destroyed, buildings either made out of brick or wood, etc., or total destruction, where we actually see the waves on the street. So again, this is based on the feedback about who's feeling it. Do you wake up in the middle of the night if the earthquake occurred? And that again, all those are assigned those values based on that. Magnitude, so that was intensity. Magnitude is often measured using a scale called the Richter scale. This is something we might be familiar with, a scale that uses numbers usually from about 1 to 10, and it's based on the actual ground motion of the largest seismic wave. So how much is the ground offset? That's the amplitude of the wave. This is a logarithmic scale, meaning that if we have a magnitude 1 versus a magnitude 2 earthquake, it's a 10 times increase in the ground motion. So each whole number represents a 10 times increase of ground motion. But for that same difference of 1 versus a 2 on the Richter scale, even though it's a 10 times difference in the amount of ground motion, that same jump from a 1 to a 2 is a 32 times difference in the amount of energy that was released during that earthquake event. This Richter scale is useful for small up to large earthquakes, but is really unhelpful when we get to the very, very large earthquakes. The scale is just not good at picking up on the differences between our larger earthquake events. So we'll see we have a different scale that helps us with that. So here we have, this is from the textbook, and it's important to take a minute to look at this. What we're looking at here is not the magnitude, but like the difference in magnitude. So for example, if we had an earthquake that was on the Richter scale, it was a 7, and another one that was an 8. Okay, what's the difference between a 7 and 8? It's a difference in magnitude of 1. Between a 7 and an 8, the difference is 1. So how much more ground motion was there? 10 times, because it was one whole number from a 7 to an 8. That is a 32 times difference in the amount of energy that was released. Okay, now let's look at magnitude 7 versus a magnitude 9 earthquake. What's the difference between those? 2. Between 7 and 9, that's a difference of 2. So there's 100 times difference in the amount of ground motion or amplitude of that wave. Yet the amount of energy released between a 7 and a 9 is 1,000 times different. So that's what that last column is talking about, the energy difference. And look at that, a difference in magnitude of 4. So let's come up with a scenario for that. We have magnitude 1 earthquake versus magnitude 5 earthquake. What's the difference in the amount of ground motion? 10,000 times different between a magnitude 1 and a magnitude 5. But there's a million times difference in terms of the amount of energy that's estimated to be released between those two earthquakes. In order to determine the size of very large earthquakes, we need a different scale. We use the moment magnitude scale, which measures the total energy that was released by the slippage or by the earthquake. And what we're doing here is we're using more variables or more factors in order to get a better estimate of those very large earthquakes. For the smaller earthquakes, there's not a difference or a significant difference in the number that we'd get for the magnitude and the moment magnitude. But again, for those 8s and 9s, we need to add in more variables to better understand the difference in energy. So we're talking about how much of the fault slipped in the area of the fault that actually ruptured at the surface, and then what kind of rock and kind of the strength of the rock that was broken in order to differentiate at the higher end of the scale. And here's our moment magnitude, and also gives us some interesting information about, on average, how many of these do we see per year. It's really interesting to look down at the bottom here. The Earth is in constant motion, it's constantly shaking. There are always earthquakes that are going on. About 1.3 million per year in the 2 to 3 range. So these are very minor, no property damage, but may be felt by humans.